Okay, we're happy to have a tutor to give us a talk on categorical DT theory of C3 and
Yeah, okay, thank you for the invitation, for the opportunity to speak here. So I'll give two talks about this categorical DT theory. So the plan will be as follows. So first, talk about I'll give an overview of Donaldson-Thomas theory of Calabi-Yau threefolds, and I'll talk about motivation of doing some of this construction. I'll explain some of the problems we're interested in and some applications in more classical algebraic geometry. Then two, I'll start discussing an example in detail. So I'll say what we know and some conjectures for sort of a complete description of this categorical Donaldson-Thomas category. So this sort of most basic example, that is points on C3. So it will be a categorical study of the Hilbert scheme of points on C3. So maybe, and then this second part will be split in two. So first, I'll talk about the Hilbert scheme of points on C2, which is a smooth variety. I'll discuss some results there. And so this will be today. Then maybe I'll just start talking about the Hilbert scheme of points on C3 today, and I'll continue on Wednesday. So then three. So some interesting problems here in DT theory are about wall crossing. So I'll give an example of wall crossing. So which would be about the DT-PT correspondence. And time permitting, I'll talk about quasi-BPS categories. So maybe part of the goal of these talks would be to convince you that these quasi-BPS categories are kind of the central object in this categorical study of Donaldson-Thomas theory. Okay, so for one, so DT invariants, Donaldson-Thomas invariants are, initially they were introduced as virtual counts of sheaves, ideal sheaves, most interesting ideal sheaves on curves, on threefolds, on smooth complex threefolds. So their definition is via a virtual fundamental class. One has a virtual fundamental class, and using some insertions, one produces some integer numbers, and they are related. So one obtains some integers, which are a virtual count. When one applies this theory to ideal sheaves, they are virtual counts of curves. On the threefold, and they are related to other enumerative invariants, such as Gromov-Witten invariants by the Maulik-Nekrasov-Okunkov-Pandharipande conjecture. Okay. So I'll be focusing on the case when the threefold is actually Calabi-Yau. So in this case, no insertions are needed. One obtains an integer right away. The virtual fundamental class produces an integer. The reason why I'll be focusing on that in that particular case is that DT invariants admit a different description, an alternative description, which is easier to categorify. So out of that description, one gets naturally a cohomology theory. Then I'll be also explaining that one also gets a DG category. One also gets a K-theoretic, a K-theory. So let me see. So when X is Calabi-Yau, there is a different description of DT invariants, basically based on vanishing cycles. So I'll just say due to Baran and other people, Joyce and his collaborators. But before I move on, I should say that what happens is now if X is a Calabi-Yau threefold, and if alpha, so maybe X is smooth, let's see, proper Calabi-Yau threefold, and alpha is a class in even cohomology, and L is a stability condition. For example, a Giesinger stability condition, such that L stable equals L semi-stable. Then one considers the stack of L semi-stable objects on X with Chern character alpha. So this is space of L semi-stable sheaves on X with Chern character alpha. And the DT invariant, it's a virtual count of such objects. And I'll be explaining in a second is a version of an Euler characteristic of this space. So as I was saying, this can be described using vanishing cycles, and this will give us the first cohomology theory, so sort of the first categorification of DT invariants. And the description goes as follows. So locally, ML semi-stable alpha is the critical locus of a regular function on a manifold, or it can be also taken a variety. Because
for a group we can, for some quadratic sheaves, why can't we do minus
okay. So you're saying you might have a finite group.
Oh yeah, so, okay. So.
Yeah.
What?
Yeah. Okay, so so locally, the space is sort of the critical locus of F on a smooth variety. See? And now on such a space, the critical locus of a variety, one has a natural sheaf. So that is the vanishing cycle sheaf of F. So I'll be explaining later the definition of this. So this is a reverse sheaf on this critical locus. So now the Donaldson-Thomas invariant is obtained out of these vanishing cycles. So one way to formulate this is due to Joyce and his collaborators. One can glue these vanishing cycles. To obtain a perverse sheaf on ML, perverse sheaf phi, and then the DT invariant will be the Euler characteristic of the cohomology of this sheaf. So instead of studying this integer, the DT invariant, one can study instead this perverse sheaf. One can use, for example, excision properties or other properties like duality or the six-functor formalism or the decomposition theorem or things like that to study this perverse sheaf, obtain some results, and then translate them and obtain results about the classical DT invariant. Also, another important fact about this description, this local description using a critical locus, is that one obtains a new cohomology theory for this singular spaces. It is this critical cohomology. So maybe all right. Actually, this cohomological DT theory studies this sheaf phi or the cohomology of this sheaf phi. So this is sort of, we think of this as a maybe replacement of singular cohomology of the singular spaces L semi-stable of Chern character alpha. So indeed, these spaces, they are singular. We'll see in the most basic case, that is the Hilbert scheme of points on C3, that we do not understand the Betti numbers of the spaces. However, through this description via vanishing cycle. Yes. But then this description via vanishing cycles provides a new cohomology theory, this critical cohomology that's more computable and will have properties similar to singular cohomology when applied to a smooth variety. Okay, so this is what cohomology DT theory is about. So again, instead of studying just one integer, this DT invariant, one studies this sheaf or its cohomology. Sorry?
The construction of the reverse sheaf is independent of
no, it depends on an orientation data. Yes. And then one obtains, the dimensions of the spaces will depend on that orientation data.
Will you have examples where you explain how that works?
Yes, I'll do an explicit example where I'll say what the spaces are. Yeah. Conjecturally, yes, but not now. Yes. Yeah. So
Instead of studying DT theory or threefold, would it have made sense to do something like Euler characteristics of infinite moduli? I mean, maybe that's too trivial, I guess. But would you be able to apply the technology to that?
But I'm not that familiar with infinite moduli. But are they local? Are they also locally?
Okay.
Actually, as long as spaces are given as critical loci of this regular function on a smooth space, one could construct this new cohomology theory, and I'll explain also this new K-theory. Okay, so maybe, okay, so this is, yeah, so we have now this new, this critical cohomology, and then there are two flavors of, at least two flavors of results in this area, in the cohomological DT theory. Yeah.
If I have like a final relative of the canonical divide,
Yes.
There was some ages ago, there was some kind of theory by Richards and Danish about how that could be also made into some kind of relative critical locus or something like that. Is that in development?
Oh, yeah, I don't think it's published. I never knew about this stuff. Yeah. Yeah. Yes.
Actually, suppose you just take a theory to describe a quiver.
Yes.
Like sheaves of D3 there's an underlying quiver variety.
Yeah.
Quiver variety, could you spell this out? Is that trivial? I mean, sure, so the BPS counts as autocorrect spaces, some known spaces, but
no.
do you have some other way of?
I think the main example of
For C3,
so
yeah.
We're going to go back to the quiver. Okay.
But that's just one example. But
just sit back and wait. Okay.
No, I think this type of no, but I think this type of cohomologies are indeed studied for quiver varieties. That would be a first case. For example, here, these Nakajima quiver varieties will give you a local description for moduli of semi-stable sheaves on a K3 surface. So they are very fundamental, but then they are not trivial. Okay, so the side of this cohomology theories for those spaces. So okay, there are at least two flavors of results in this cohomological DT theory. So the first one is more like an intrinsic study of these spaces, moduli of sheaves on Calabi-Yau threefolds. So maybe, so instead of now just one number, one has a sequence of spaces, a graded vector space. One could study those numbers, see what it says, or one gets new information about moduli of sheaves on Calabi-Yau threefolds. So I'll be explaining one such computation later today. Another direction is to use dimensional reduction. And I'll be explaining this in a second, to obtain results about more classical cohomology theories. Okay, so like singular cohomology, Borel-Moore homology, for moduli of sheaves on a surface. Okay, so this second direction is maybe more interesting to people not working in DT theory, but working in more classical algebraic geometry. So now I'll be explaining this dimensional reduction story. So let S be a surface, smooth surface. One can consider an associated Calabi-Yau threefold, which will not be proper, but still we can still consider this DT invariants there. So it will be the total space of the canonical of S. Right? So this is what is called the local Calabi-Yau threefold. And then we can consider alpha a class on S, a homology class on S. Then maybe stability condition on S. So then we'll obtain spaces of semi-stable sheaves on S and X. So this dimensional reduction says the following. That there is an isomorphism between this critical cohomology and, okay, so if I don't assume anything about S, then this would be Borel more homology of ML semi-stable S alpha. Yes, thanks. Yeah. So this will be compactly supported sheaves. Yes. So now both of these. Yeah, thanks. Yeah, for both S and S. Yeah. As opposed to Z coefficients. And, let me see. Yeah, I think this sheaf is defined as a sheaf of Q constructible sheaves. But indeed, so phi is this vanishing cycle functor that's applied to Q constructible sheaves, but maybe it could be applied to Z constructible sheaf too, in this particular case. So yeah, I don't know what happens there. Okay. So what this so it compares two cohomology theories, one for the threefold, one for the surface. One is this cohomology of this new sheaf phi, but the one is a more classical theory, so it's like Borel-Moore homology. And well, so this space is singular in almost all cases. The space on the surface may be singular. The advantage here of studying this sheaf phi is that it is perverse. So even if the total stack is singular, the sheaf is perverse. We have some tools of studying it. So, for example, duality, but also maybe the main tool would be the six-functor formalism or the decomposition theorem. And then the idea in using this dimensional reduction is that even if this space is very singular, because we take this cohomology of this perverse sheaf, we may be able to understand the support of this or some properties, and then transfer information to the surface side and obtain results about more classical cohomologies, but defined on the surface.
So this phi is a very special sheaf.
Sorry?
This phi is a very special sheaf.
Yes.
And its support is not simply S, it's something else.
No, it's not. Yes. Yeah. I'll also mention this for the C3.
Is there some way of expression? But you'll tell us about phi.
Yeah.
But is there some? Can I is there some just push forward map that pushes forward the two spaces, or is just the global map?
No, you're right. Yeah, it's given. Yeah, in the local case, it is given by a push forward. So this will be the zero locus of a section. Right. Yeah, push forward. So first it will be the push forward in the total space of a vector bundle. Yeah.
So saying something like there's a push forward map in this moment. From X to S.
Yeah, this way.
That way?
Yes. Yeah. Yes. Yeah, but then the sheaf phi is not just push forward of Q of that. So the sheaf phi is more complicated. It's not just supported on the S, on the image from S.
So then, if there's a map this way, is that correct to say that there's like push forward of Q this way, then the more DB goes to that phi? DB constructed will be
No. Yeah.
So what's the idea then of dimensional reduction?
Well, yeah, so you can compare something on the threefold with something on the surface, but the theories, the cohomology theories are different. So here it's, this more classical, like singular cohomology or Borel-Moore homology, but here it's the cohomology of a certain, of a new perverse sheaf.
Something that is this way,
No. I was saying that this sheaf, maybe it's not the image of a sheaf on S, but yeah, this statement, after you apply, if you take cohomology of the sheaf, it comes from S. Yeah.
But only after you take cohomology.
Yes. Yeah. Okay.
Confused, like you have the space X and S. You also have the modulus space of sheaves among these two guys.
Yes.
So I understand is the X is the bundle over S. What's the ratio of the modulus space?
Well, maybe.
When you look at sheaves on X, you look at sheaves on X that would support an X?
Yes.
Yeah. So maybe. Okay. Let me see what this. I mean, it's not. In general, it's not. It's not the case that this is just a bundle over this. So what? I mean, maybe. Okay. So what happens is that this is an example of a quasi-smooth scheme. It's a this derived local complete intersection, and out of that one can construct a cotangent space. You can take the -1 shifted cotangent space of that, and this space is the classical truncation of that. I don't know if this is very enlightening, but.
Then there is a zero section. And then you take sheaves associated to the clusters of sheaves of that zero section. And then the modulus space will contain something that's not zero section, so zero section can move around. But the sheaves in the zero section will be exactly the modulus space in the right hand. And then you come back to the top and that moves around.
Okay, maybe we
Yeah. Yeah, I think maybe this was just supposed to be this sort of heuristics that you can compare a theory on the threefold with a theory on the surface. So let me see. Okay, so then next I wanted to say some results where, so as I mentioned in this cohomological D theory, there are at least these two directions one can go. And then two is maybe more interesting to people not doing enumerative geometry. So then I wanted to mention some applications of this dimensional reduction to problems not in enumerative geometries. So maybe A. If S is a surface with omega S trivial, so for example, S is C2 or K3 surface, or then one can consider the, maybe let's say compactly supported cohomology of the spaces of semi-stable sheaves. Yes, okay, so this will be in general, so here L semi-stable may not be equal to L stable. So in general, this space is a singular stack. So it is not a variety. But still, one can consider this classical cohomologies. Then it has a mixed host structure by work of Delin. Depending on the surface S, this space will be singular, but may also not be proper. For example, if S is C2 or if it's a local curve. But then the theorem is that the mixed host structure is pure. So, of course, smooth and proper varieties have pure host structures. So from the point of view of host theory, these stacks of semi-stable objects on the surface behave like they were smooth. So this is a conjecture of Halper-Leissner.
Pure means what?
So it's a pure as a Hodge structure. So yeah, so maybe the kind of the point here is that this smooth and proper varieties have these pure Hodge structures, whereas just an arbitrary variety will have usually a Hodge structure built out from these pure Hodge structures. But here, yeah, the statement is that it is pure directly, so it's similar to one of a smooth and proper variety. No. So I said that the Lean constructed this mixed Hodge structure, so more general varieties. So then, yeah, this. Okay, so in this particular case, it was conjectured by Halper-Leissner that these mixed Hodge structures are actually pure. Then it's proved by Davison using this cohomological DT theory. I mean, yeah, so the proof that Davison gave is, again, kind of one reduces it to a local study of the spaces over a good moduli space. In that case, it's given by this pre-projective algebras. And then he just shows that those are pure for pre-projective algebras, not for a general quiver. So B, it's an application to what's called chi-independence. So one version is if S is a toric Del-Pezzo surface. And then beta is a class on H2S. And then D and D prime are integers. Okay, maybe yeah, L is a line bundle. Then one can look at, yeah, so I should say that, so now this is a stack of L semi-stable sheaves of support beta, so the support will be most one-dimensional and Euler characteristic D, and this will have what's called a good moduli space, so a coarse space. So something as going from a quotient stack to V mod G to G invariant on V. Then the statement is that these spaces, beta D, they have the same cohomologies as D varies. So the intersection cohomology of this is isomorphic to the intersection cohomology for the space of L semi-stable sheaves of class beta and Euler characteristic D prime, for all D and D primes. So it says that these two moduli spaces, even if there is no obvious geometric way of going from one to the other, then they will have the same, so this is intersection cohomology. Then they will have the same intersection cohomology. It's the Euler characteristic of the sheaves. So this space parameterizes sheaves of support beta and Euler characteristic D. Yes. Okay, so so this is very different from what happens in the curve case. In the curve case, the beta will be replaced by the rank of a vector bundle. Then, if you look at stable rank R vector bundles of Euler characteristic D and D prime, they will not have this property. Their singular cohomologies are not the same. However, for S Del-Pezzo surface, this phenomenon happens. So this is called the chi-independence phenomenon. So this is proved by Mauliksen. Yes, yes. So this beta is in H.
But over there, when you have the dimensional reduction, on the right, you don't have the intersection component, that's cube, right?
Yes. Yeah. Maybe C. So if C is a smooth projected curve, of G is greater or equal than 1, then R is rank, and then 1 takes two integers, D and D prime, such that the greatest common divisor of R, D, and the greatest common divisor of R and D prime is 1. Then one can look at the moduli of semi-stable Higgs bundles on the curve C of rank R and degree D. And in this case, one can ask a similar question. So as I said, if you don't study Higgs bundles, if you just study vector bundles on a curve, these two spaces will not have the same singular cohomology, but they have if you consider the Higgs spaces, they will have the same singular cohomology. So now this statement is not true for intersection cohomology. So I have to take either singular cohomology for the spaces that are both smooth, or a different type of cohomology theory called BPS cohomology if I don't want to impose this condition that the greatest common divisor is 1. So this is proved by Kinjo and Koseki.
Sorry, are there two spaces that have the same dimension?
Yes.
But they're still not the same?
No, no. Okay, so these are some sample applications of this cohomological DT theory, where the statements do not refer to enumerative geometry, things like that.
Are there matched between the spaces?
No.
So this equivalence is not induced. So how does the equal sign come about?
Well, so this is just an isomorphism, maybe, of vector spaces, if you want. Actually, it's more than that. Also, it preserves the whole structure. Yeah, the way this proofs work is both these spaces admit a map to a common space, each in this. So then you study the decomposition theorem over that, and then you show they have the same support. Supports do not depend on this Euler characteristic, more or less. Okay, so yeah. So then yeah, so this is what I want to say about cohomological DT theory. So now one can wonder if this also cohomological DT theory comes from a different object. So if it can be categorified one level up. So is there a DG category DT L X alpha, which recovers this cohomological theory? By which I mean, for example, one way to interpret this is that if you apply the periodic cyclic homology, okay, so this is some sort of de Rham cohomology for the subjects, DG categories. If one takes the periodic cyclic homology of these categories, is it true that this will be H I plus 2J, J in Z, ML semi-stable, X alpha phi? So the question is, So this periodic cyclic homology is periodic mod 2. So there will be just it's determined by the value in 0 and 1. Then the question is if these two values recover the mod 2 periodic cohomology theory that we previously studied.
Is there something like that for this critical local function?
Yes, yes. Now I'll explain. Yeah.
Like the twisted
So it's matrix factorization. Okay. Yes. So then, okay, so this. Well, HH is, well, HP is maybe simpler than HH, right? HH is more like the Durham complex, then you have an extra differential, and then you take HP of that. I don't know, that would be an answer. No, I said periodic cyclic homology. I think it's easier. Well, I don't know. I mean, you get this way. You get this version of the RAM cohomology for a DG category as opposed to the RAM complex. So this is easier.
So there must be some extra data you need in order to define HP.
HP, yes, for any DG category. Yeah. Yeah. So now. Yes. Yeah. So this is what I would say. So now in the local case, we know what this category should be. So what do I mean by local case? So if f is a regular function on a smooth variety, then one can consider the category of matrix factorizations. I'll also explain later the precise definition of this. So this is just a DG category. Then okay, so this category works. So, which I mean, it's periodic cyclic homology. Yeah, sure. So. We'll recover the mod 2 periodic version of the cohomology of vanishing cycles. So this was proposed by Kontsevich and Soibelman. That is, this categorification of vanishing cycles using matrix factorization was proposed by Kontsevich and Soibelman, and this statement was proved by Efimov. When? So I think maybe they proposed it 2009, and Efimov's paper was on archive. So then, yeah, as Andrei said, of course, it's important to glue this category. So we know, again, this moduli of semi-stable sheaves on a Calabi-Yau threefold locally look like critical loci of such functions. So we know what we have all these objects in this local case, but then we need to glue them. For the constructible sheaf pi, this was done by Joyce and his collaborators, but it's highly non-trivial. And this is not known for this DT category. So this is an important problem. Yes, yes. So this is why we can study C3 in detail. Yeah, so an important problem is to define these categories. So to glue categories of matrix factorizations. Yes, yeah, they will have strong generators, yeah. So I think, yeah. So maybe this is at this last part on Wednesday when I talk about this quasi-BPS categories, is that these categories admit semi-orthogonal decompositions and all the pieces behave like, they're coming from smooth varieties.
What is this HP? What is the meaning of this HP?
HP is some gadget we want to extract from.
What is the gadget?
Yeah, so this is what. So we want to extract out of a category this cohomology theory. No, I don't do that.
So what is it supposed to do with the objects, and is it like taking K-theory process, or what is it supposed to do?
It's so.
So what is it supposed to do?
So a DG category is. So a DG category is something like a.
What did you forget?
Yeah. So. Yeah. So anyway, yeah. So we think of DG categories as being some geometric spaces, and then we would like to have some version of singular cohomology for these spaces. So same way, if you take X variety, you want to recover the singular cohomology.
The DT category means what? That you have some differential that has some morphism?
It's just a object, the morphism space is like a chain complex.
Okay. Well, sorry, isn't it a morphism space of chain complex?
Yeah, it's usually what we have it.
Yeah. Okay.
Yeah, so then a question was whether for these new spaces, for DG categories, one has a cohomology theory that behaves like singular cohomology, by which I mean if you apply this HP to the natural DG categories associated to a variety, like DB co X, you get singular cohomology. Yes. Okay. Yes, yeah.
In the case for HH of the
But so maybe yes. So we have this world of DG categories.
Well, why is it a useful thing to have? I mean, it seems to forget like everything. I mean, what's the use?
Tudor wants the opposite. Tudor wants to reach.
He wants to go backwards. Okay,
Yeah.
that's the game.
Yeah.
And this is supposed to be the model. Is that somehow I'm supposed to understand?
Yeah, exactly. It's supposed to be like some kind of Durant theory for this space.
Yeah, so we kind of have, we already have this answer, this singular cohomology. So that is, we have this vanishing, or whatever it's called, critical cohomology. Then a question raised by these people was if there is a natural categorification. So by which I mean a category like this, but the way we think in algebraic geometry is that this is a space or non-commutative space. So do we have a natural space from which we recover all this stuff? Then, we could study this space instead. Then we would, by studying this space, we'll get new cohomology theories. For example, by taking K-theory of this, but we can just study it for its own sake and recover structure about the initial moduli spaces of sheaves on a threefold.
the sheet of phi, right? It's only supported on the critical loci.
Yes, yes. So this, yeah. So this, so before I abuse notation and I wrote critical F here, but. Okay. Okay, so as I said, yeah, so this is kind of a central problem. We don't know how to do this yet, so but it is known how to define it in the case of a local surface. So when X is the total space of the canonical over a surface S. So anyway, let me see. Okay, so okay, so maybe now I should say that this so categorical DT theory would be the study of these categories. Okay. So as I said, they are not defined in general, but they are defined when X is the total space of the canonical over S. So one type of problems is, again, this intrinsic study. So one, for example, one gets a new sort of new structure for moduli of sheaves on X. For example, one gets a version of K-theoretic DT spaces. By taking their dimension, one gets a version of K-theoretic DT invariant, so which is different from the version studied by André and his collaborators. But then other problems are sort of, kind of the fundamental problems one also has in DT theory. That is, what happens when you vary the stability condition. So this goes under the name of wall crossing. So vary L and understand how these categories change under the change of a stability condition. Then and other problems are also sort of categorify other enumerative invariants. So such as this BPS invariants or DT invariants, Pandharipande-Thomas invariants. And then we'll see that trying to understand the categorical analog of this BPS invariant produces interesting examples of this DG category. So as I said, we think of this as some non-commutative spaces, but in many interesting cases, this sort of BPS, this categorization of BPS invariant will be some smooth and proper categories that will be resolutions of interesting spaces. So this is kind of this intrinsic study. And then another direction is, again, use dimensional reduction.
So just making sure I understand the clarification. So you had some space, modular space, and you locally select the matrix critical loci and pull up the matrix factorization
Yes.
into a global category.
Yes.
And that's supposed to be categorized to go every other invariants on this space.
Yes, yes. So it will recover this mod to periodic, mod to critical cohomological. No. Oh, no, but they are two different things. So, well, yeah, one can consider C** invariant matrix factorization, but then the periodic cyclic homology of those categories will again be Z mod to periodic. Well, I say that maybe no. So there are varieties that have the same derived category, but then they do not have the same singular cohomology. One needs to modify it somewhere. This dimensional, so as I said, yeah, one direction is this intrinsic study. The other one is again to use dimensional reduction to obtain statements, obtain results about more classical categories for moduli of sheaves on surfaces. So now I'll give two examples of such applications. So maybe A. So if S is a K3 surface and alpha is an even homology class, and L and L prime are two stability conditions, on S, such that L semi-stable is the same as L stable, and also L prime semi-stable is the same as L prime stable. Then if we consider these two spaces, so one is of L semi-stable sheaves on S character alpha, the other for L prime semi-stable sheaves S character alpha. In this case, yeah, maybe I'm abusing notation, so I'm denoting by the same symbols above the stack and the corresponding good moduli space. They will both be smooth hyperkähler varieties. And they are derived equivalent. So if one takes the category of coherent sheaves with the spaces, one gets a derived equivalence. No, but I think he kind of uses fundamentally the Donaldson-Thomas perspective because he reduces it to a local computation about using matrix factorization, which is basically this. So locally he looks. He considers a Calabi-Yau tree object. So this is why I include this example. Yeah. So this was interesting because it proves cases of conjectures of Kawamata and Bondal-Orlov. Yeah. It was proved by Alper Leissner. Yes, there are definitely choices on how you go, because it's a wall crossing statement. So you need to go from the L chamber to the L prime chamber. Yeah, I think it's sort of the fundamental group of the hyperplane arrangement, something like that. B, if C is a smooth projective curve of genus G, then one can look at the symmetric power of C. One can study, so in this sort of the world of these DG categories, one important problem is decompose the category in pieces that cannot be further decomposed. So for example, one can take the category of coherent sheaves on this space and try to produce such decompositions, and using this wall crossing, then this categorical DT theory, this was done by Toda. A semi-orthogonal decomposition of dB of this category in dB of X0C and C, E, C, where E is less than the genes.
I'm sorry, can I just stop you for a second? I'm still not entirely understanding this philosophy. So, suppose we study coherent sheaves on X.
Yes.
Then you already have some category of objects.
Yes.
Now, what we'd like to do is we would like to categorify the Euler characters of modular spaces of these very sheaves.
Yes.
And how is it supposed to interact with the original without category, which knows everything, which distinguishes like the different points in their own modular space? Is it supposed to be something new, or I mean, you start with something which knows everything, then we throw away a whole bunch of stuff because we just take the Euler character of the modular space of the object. And now I'd like to go back to some kind of category.
Yeah, let me see. So I think.
They could replace it with a direct category of this multi-space of sheets on the axis and stuff. For the multi-space of sheets on X, it's very similar. It has many components. So the virtual.
Why do I mean?
So this category is actually should be like a virtual category of multi-space of sheets.
I don't want to go back to the full original category where my objects were the sheets. I don't want to do that. But the idea is that there might be some category of completely different flavor.
Yeah, I think. I would say, yeah. Besides that, this sort of this type of categorization, they also are natural from the point of view of representation theory. So then people they have this whole algebras, then one has that they are sort of geometric realizations of quantum groups, and then I think so. In that case, a categorization has already been studied by Lustig or other people. So then a question would be: is there some other category there?
Yeah, but think about it like this. Suppose they studied like this at the point, and then like modular spaces of like instant objects on L4. It's an interesting thing. It's a very interesting geometry. Very interesting geometry of that space. Now instead of using 6 complex dimensions, that this modular space is supposed to be like instant objects on L4. That's a very single option. And what Tudor proposing for that is the replacement of like sheaves on that object on the modular space.
Wait, I thought I wanted to categorize by the other characters. In other words, I just want to clone here.
No, if you want to like the whole, you take the whole space, and then you like compute, as much as you want about that modular space. What is logical is you bigger than you can about that model. Slope can look like this kind of under consideration.
I want to go back to the category on the modular.
Exactly.
Is that modular space? I just think like if you suppose you have some space and you want to study like maps from some space to that target space, and then you want to study the vector space. The modular space, let's say, have a category and I want to study the family of objects in that category. I thought quite big practical into other categories.
I think there's any kind of basic things. It's just you try to somehow trying to say something global about modular space and modular space
and the model for this is that with the gather that you got non categories with X and then the other categories with modular X.
Yeah.
We want to be able to do for all of our X's we can modularize this sheet of people.
Yes. Yeah. Okay. So maybe I should have started with the example. Okay, so let me see here. So yeah, now the plan is to talk about this example of C3. So then we would like to parameterize sheaves with proper support of C3. So the only possibility is sheaves where the support has dimension 0. So the relevant space will be the Hilbert scheme of D points on C3. Okay, so then so this space is very singular. So very singular for the greater than 4. So we do not know the number of irreducible components. Do not know the dimensions of irreducible components, so on. But still, we would like to understand some versions of its cohomology theory. So then there are some fundamental versions. So it's cohomologies. Because this geometry is really badly behaved, we have there is no possibility to understand right now the Betti numbers or the singular cohomology. So this DT perspective, these categorifications I mentioned above. So this DT theory proposes sort of modifications of the usual cohomology theories. So actually, the Euler characteristic can be computed, but we can also look at this DT invariant. But instead of singular cohomology, we replace it by this this critical cohomology. And we'll see. So again, whereas this is not computable right now, this we'll see that this critical cohomology is computable.
So, say, total number of irreducible components, is it finite or not?
It's fine. It is fine. And then, so also it's K-theory or its category of coherent sheaves. These are, again, complicated because of the singularities, but this DT theory tells us to replace them by certain objects, by theories that are computable. And not only that, but we'll see that we'll get the sort of dimension 3 analog of what these classical theories, so maybe I should say so. So using these new theories. We get the dimension 3 analogs of the usual theories, that is singular cohomology, K-theory, and DB-Co for dimension 2. So I say that this is one reason to consider these cohomologies.
Suppose someone give me a singular space, and I can have two objects. One is to the magical DB-Co of that single space. Another is suppose I know this single space is the loci angle with respect to the how do I know which one is the correct choice?
Oh, well, I think if the space is singular, maybe a lesson or a message of this talk is that, yeah, you should take matrix factorization. That's better behavior. I think that's a good question. Yeah. Yes. Yeah. Indeed, in general, there might be multiple realizations, and they will not be direct equivalent, or they will. Yeah. Okay. So now the plan. I don't have much time left, but. So now the plan is to explain what these classical theories are in dimension 2, so that we know what we want to get in dimension 3, or get you a sense of the results in dimension 2. So talk about the Hilbert scheme of points on C2. So of course, the main difference between this space and the Hilbert scheme of points on C3 is that this is smooth. It's also connected. Okay, so then going here to this cohomology theory. So actually, before we discuss singular cohomology, we can ask what is its Euler characteristic. Sorry? So one way to compute the Euler characteristic is to use scaling action on C2. So there is a two-dimensional torus acting on C2, and this action extends to an action on Hilbert C2D. I'll denote this torus by T. Then this Euler characteristic will be the same as the one for T fixed points on Hilbert C2D. So now Hilbert C2D parameterizes. This is the Hilbert scheme of D points. So parameterizes ideals I inside the structure sheaf of C2. So these are polynomials into variables of co-length D. So an ideal I in CXY is T fixed if it is generated by monomials. So now this ideal I's will correspond to partitions of D. So as follows. So in the first quadrant, we can look at the lattice points ij such that xi, yj is in this T fixed ideal I. Then the complement of the set of all these lattice points will give us a partition of D. Okay. So what happens is that the T fixed locus of the Hilbert C2D is given by points in bijection with the number of partitions of D. So I'll denote this number of partitions of D by P2D. So then the Euler characteristic of Hilbert C2D is equal to P2D. Now we can ask, what about Betti numbers? So sort of to tell us the dimensions of singular cohomologies. To do this, one can use the same action and the Aliniki-Birula decomposition. So by considering the attracting loci for a generic C star inside T, we apply this decomposition. So this works because Hilp C2D is smooth. But we obtain that we obtain a stratification of Hilp C2D in a cellular stratification, so a stratification in affine spaces. Okay. So this is very special. So most varieties do not admit such nice stratifications. But now, so right away we get that the odd Betti numbers are 0, and then the even Betti numbers are given by the number of cells CA used in the stratification. And this can be also computed using partitions. So if one computes the dimensions of Borel-Moore homology of the space, it will be the number of partitions of 2D minus K in parts at most K minus D. Well, I think this is the point of the talk. So the point of this project. Well, it's not that easy, right? So the issue is that this space Hilp C2D is Hilp C3D is singular. So, for example, you cannot use this BB decomposition. Yeah, kind of.
Can you have a picture in mind? What does it tell? What does it look like? It's obvious.
Yes, yes. So
or a prescription. What is exactly one is one counting?
So it's so I said this is the number of cells CK, sorry, used in this stratification. Or should I write a formula?
I know the formula is not interesting.
We know the extent of the space. You choose any kind of parameter shuttle test with arbitrary, right, and so forth. But every point will have like you have to put out like a number of pulses.
I see the tracking.
And so
I see.
So
It's not the usual thing.
this the cell is open to vector space.
No,
You can have many different formulas and they will be all be equivalent.
So any other questions?
Are you going to relate it to the vanishing cycle?
Well, yeah, this was the plan. So, so this is the story for Hilp C2D. So this is the story in the two-dimensional case. Then, as I said, in the three-dimension, if we just try to compute the singular cohomology naively, yeah, we cannot do that. So then we'll put the vanishing cycles in, and then. Yeah, besides the characteristic, yeah. But I think I'll do that next time. So I ran out of time today. But okay, so maybe how much time I have left? 10 minutes. Yeah. Then so these are the Betti numbers. So then sort of the next cohomology one may consider is K-theory. So for a general variety, this is more complicated to compute than a singular cohomology. It's usually infinite dimensional, and it's not a topological invariant of the underlying space. But in this case, because this Hilp C2D has such a nice stratification, it's actually easier to compute than the Betti numbers. So, well, I will also always compute just the zeroth level.
Don't we just give you the field?
Yes, yeah. Well, I think we can compute it in terms of the K-theory of the field. Yeah. So this will be a free z-abelian group of rank P2D. So this follows from the excision argument and using the cellular decomposition. So then next, instead of just computing individual cohomologies for a given space, one can wonder whether there is a gadget for which this cohomology is factor. So there is a more universal cohomology theory. That recovers singular cohomology and K-theory. So one such gadget, one gadget that almost does that is this category of coherent sheaves. But that recovers topological K-theory, not algebraic K-theory. So here, I mean algebraic K-theory. Yeah, okay.
Actually, this category for actual Calabi-Yau threefold, does this would be more like, does this K-theory you're going to compute for an actual, like for a critic threefold, will they have some kind of, will they look like topological, or will they look like some kind of tensor stuff?
So sorry, which K-theory? That's
you're aiming to have some, like for example, K-theory of moduli of sheaves or whatever, like critic threefold.
yes.
Would you expect it to look, this K-theory like a topological K-theory or like an algebraic K-theory?
No, like, yeah, algebraic K-theory. So it will be, yeah, very infinite dimensional. So it will contain this Chow groups of many copies. So, yeah, maybe I think best, the ideal scenario is that you'll be able to decompose that K-theory into K-theories of the quintic itself or symmetric powers of the quintic itself. But those should, yeah, are very infinite dimensional. Okay, so there is this object, this category of coherent sheaves on X, this dBx. So as I said, this is kind of a gadget that recovers singular cohomology. So X is just let's say a smooth variety. Maybe why just. So it recovers a mod to periodic version of singular cohomology through periodic cyclic homology. And yeah, the K-theory of this category is the same as K-theory of Y. So, given a variety Y, one can study this category dBY, so it's sort of this maybe universal cohomology theory. Yes, it works if one takes T equivariant complexes. Yes, yes, for that it works. Yes, but not for not equivariant complexes. Yes. So one can study this category dBY, and then kind of the way this process goes is in two steps. One is decompose it in decomposable pieces or in decomposable summands. And then two, well, study those summands separately. So, by which I mean, well, then the K-theory of Y will be the sum of K-theory of this indecomposable pieces. So if you're just interested in K-theory, you can just try to understand the K-theory of this indecomposable.
Indecomposable pieces of what? So my example of our Y is our Hilbert system, right?
Yes.
Okay. And indecomposable pieces of who?
Indecomposable pieces of this category, dBY. Yeah, so given a category, D, one can look at decompositions, for example, AB into categories AB. The following, so
Have like no morphisms from one
yes,
part to another.
yes, no
In
more.
both directions?
No, just in one direction. Yes, yes. So you want the objects of these two categories to jump. Yeah. So then, if we have this, but then A and B themselves do not admit such decompositions, we'll say that A and B are indecomposable. They are building blocks of this category. And then the second step is to study these summands. So as I said, if you're just interested in the K-theory of Y, just study the K-theory of A and B, or for example, relate them to dBz for Z some other space. Kind of, yeah, many results in the study of the right categories do one of these two steps for given varieties of interest. Okay, so I'll just mention what happens if we do these two things for HILP C2D, and that would be the end of today's talk. So then next time I'll just focus on HILP C3D. I mean, especially this K-theory, K-theoretic study of that. So for HILP C2D, so for one, there is nothing to do because this is indecomposable. And then two, maybe related to some other spaces. Then an answer for two is given by this theorem of Bridgeland, King, Reed, and Hyman. This is kind of the main theorem about the category of coherent complexes on the Hilbert scheme of points on C2. So this HILP C2D is a resolution of singularity of sim DC2. Another resolution of singularities of sim DC2 can be obtained by taking, so instead of unordered D points, you take ordered D points, and then you take the stack quotient by sigma D. So this is a DM stack or orbifold. And they are both Krappen resolutions. So by this Bondal-Orlov-Kawamata conjecture, one would expect this to be derived equivalent. So if you go to this world of DG categories or non-commutative spaces, they are the same. And indeed, this is this result. So it's this dB HILP C2B is isomorphic to dB of the stack.
In the same category, it's also the single topology should be algebra is all of it, or any non-singular reality. This is what this is stack, this is similar SD similarity function.
Yes.
That has deformations. The unique algebra.
Yes.
And then and they also hold the
I see. Yeah, I think this is work of this loss, Bessel-Graphic over Losseff, or yeah, yes. Yeah. Okay. So kind of these are the results I wanted to mention about HILP C2D. So we have this computation of Euler characteristic, and then because it's smooth and it has this nice action of torus, we get a cellular decomposition that helps us compute its K-theory or the Betti numbers. And then lastly, one can look at this category of coherent sheaves, then do this two-step procedure. Then the main result about the study of coherent sheaves is this theorem of Bridgeland, King, Reed, Hyman. So on Wednesday, I'll talk about the analogous results, analogous constructions for HILP C3D. A conjecture, but which is in progress. At least part of that we know. Okay, thanks.
Are there aspirational universality statements for this like DT category? Like
it should be the category that has a functor from moduli of category 1 sheaves. I guess maybe on this question of there being two non-deriving congruent matrix factorization categories related. Are there helpful?
No, I think even for yeah, even if you fix X, you fix Chern character alpha, stability condition, then there is also this, there should be this notion of orientation data that will tell you how to glue those categories of matrix factorization. And I think, yeah, in general, there should be no unique such data.
You did say that conjecturally there should be a right choice of orientation?
I think that's the conjecture in cohomology. I have no idea about this DG category. Like, I mean, even for a point, you know, you can do a sort of yeah, matrix factorization of a point with zero potential, or matrix factorizations, yeah, for A1 and X squared. Okay, they are not the same category, but you can do.
Would you imagine that? Global function of cohomological category is something like that in the because of the globalization over the scale.
Right. You won't have a sheaf-off, co-sheaf-off category being over your singular space.
And do you expect some stuff like this to happen?
Sorry, so a sheaf over. So this is the sheaf of categories over a good moduli space. Yes, yes, I believe, yeah, there should be a sheaf of categories on the good moduli space of this text. If maybe there should be some conditions on the stability on the Chern character such that a good moduli space will exist, but yes, then I would believe. So then I also kind of hope that, so there should be some technical checks, but that there will be a constructible sheaf of K-theories on that space.
And then, in principle, if you have, so like no reason, you would imagine that there is, you know, why would there be some kind of canonical gluing? I think you should have been able to twist it by any kind of local system on that space. Why does that have to be, speaking of getting the best possible gluing, why there should be that? Well, there was some kind of sheaf of stuff that was that. Yeah, the local system of community should be able to twist it.
And you're saying that in cohomology, sort of this twist will be something like the cycle class of this line model, which is 1. So maybe in cohomology you don't see this phenomenon.
I mean, you twist it if it's a choice of some kind of orientation. You twist it by a kind of plus minus effect, like by a finite source.
Yeah. I'm not sure what to believe about it. Yes.
So sometimes with the DT on C3, what's more interesting than maybe just a single invariant is actually that the whole generating function enjoys some nice property.
Yes.
Does your stuff give like some categorical level version of the statements on generating functions, or?
Yeah. Rationality, you mean? Or?
Yeah, or like this. I mean, if you take all these together, the generating function is modulus.
Yeah, one can compute, yeah, this generating series, but also at the level of categories, one has an action of a certain algebra on the direct sum of these DT categories of points on C3, which I did not yet define. So then they appear as a representation of some algebra. And then if you pass to K-theory, you can sort of double that algebra to get a full quantum group. So for example, you get an action of the Heisenberg algebra on the K-theories, or equivalent K-theories of Hilp C3D. So this is sort of dimension 3 version of yeah, this theorem, celebrated theorem of Nakajima-Groshanovsky, that Heisenberg algebra acts on, if you want, the Riemann homology or Grothendieck group of Hilp C2D. But then, is this what you want to refer? No, is this what?
Yeah, this would be the question. So the theory that we talked about, do you use some new insight on this? Because this is like studying space one at a time. We put it have done this before. You don't need it. So the new thing presumably would be like what?
Yeah, my original question is even more like the true question is even more vague. I mean, in some sense, like invariant DT theory and T3 K-theoretic is supposed to tell you something about index of M theory, some preferred, kind of looking at just perturbed sector. So I would naively hope that you could categorify, the theory, integration over schemes or whatever, and somehow this would tell you something about.
Yeah,
physical over space.
yeah, I don't know.
But if your surface was not C2, but like P2, that has a similar total decomposition, would that DT call would also have a similar total decomposition to your decomposition of the surface?
Sorry, so you said that if we do
P2.
Hilbert scheme of points on P2. Yes, that's a good question. I should know the answer. That should not be composed. That should have similar total decompositions. I don't know on top of my head.
Maybe. Oh yeah, that's an example. So, Q1 is the conversion of zeros.
Okay, maybe one question. So I heard that, for example, Anatoly Kriegel has been working on matrix factorization in a sheet quality. Like, you can do matrix factorization like a sheet. Then the global section can recover from the restriction of local pieces.
I'm not sure.
Okay. And another question is like.
But sorry, what
But that was just a comment. Like there was something about matrix factorization, going up matrix factorization.
If you have some sort of Zariski cover of X, or yes, this is known. Yeah.
But this is not related.
No. In this, so that's called kind of you have two matrix factorizations on U and V, and you want to glue them to get the matrix factorization on the union. Here it's more like you have two categories over U and V, over two open spaces in the cohomological, and you want to glue the categories. Yeah.
Maybe another question is like, you have something intrinsic, like on cohomological level, you have some critical loci, you have some vanishing cycle sheet on the critical loci, and then from that you can start business and do something. The vanishing cycle cohomology. Something very intrinsic in critical loci. And do you imagine there's a categorification of that vanishing cycle sheet on your space, singular space? Maybe that answers the matrix factorization.
No, so you mean so for vanishing cycles, if you take the stock of vanishing cycles, there's a relation with the Milnor fiber, or is this type of statement?
I mean, on the cohomological level, you have your singular space, and you have your vanishing cycle sheet, the perverse sheet on your singular space.
Yes.
And then you can compute what you want. You don't have to talk about the Appian space. Yeah, right? And here I'm asking if you can replace the perverse sheet, this vanishing cycle perverse sheet, by some categorical thing. Okay, maybe that's
I mean, I think that so you want so you know that sort of you have the critical locus of f on x, but you want a category just defined using objects on this critical locus, not on x. Yeah, I don't know the answer. I don't know what people would expect. But indeed, these magic factorizations have the property that any objects are supported over the critical locus of F. More than that, I don't know. Yeah.